Yeah, I need to get these tightened.
Oh yeah, they look a bit loose.
I need to get new glasses.
Do you? Are you?
No, it's not the number, it's the style.
It's just the style. I like the style though.
Really? I don't like
Yeah.
it. It looks really bad.
It's pretty nice. It's pretty nice.
Yeah. Yeah?
Subject to our entire conversation.
Everybody, 4240. Everything.
Sounds like it.
Excitement over. Now you can lay back and breathe in the rest of the math.
Oh yes.
Everything we
My
did
favorite
so
side.
far today is in this part that matters,
Oh god.
in a sense. That's all you have to remember. Not hard. I think it's important to see where this comes from. That's why I wanted to specify one. Ideally, it helps in understanding. But just remember what it is. Relative error, unknown. Sandwich between kappa times relative residual, 1 over kappa times relative residual. Now we go back to our question. This is small, relative residual, that can be calculated. You might think if that's small, that means that this is. Is that correct or not? And I said, maybe it depends. What does it depend on? We can answer that bit at least. Condition number. If the condition number is small, then if that's small, this is small. It's in a small sandwich. Imagine the condition number is 10. This will be 10 times the relative residual. This will be 1 over 10 times. Already it's giving a hint. Suppose the condition number is 10 to the 6. This will be 10 to the 6. This will be 10 to the minus 6. And therefore the sandwich is now 12 orders of magnitude in between the thing we actually are interested in. So knowledge of this is useless in that situation. And that's why a small condition number is so important. Because you can end up, if the condition number is not pretty small quotes, 100, this won't tell you anything. Any questions? Let's do a problem. It's the same A as before. This is again in the purple book, but the details are not included. It's 3.11 UA. These are the same, and often on an exam problem I'll combine these two into one using the same matrix. So we already calculated some of the things for this part, like the condition number and stuff like that. We also know the exact solution is 1, 1. That was given, we may have to calculate it. And in this, we suppose we've done some numerical method and we've got an approximate solution. Minus 1, 0. It's not very good. And what does the inequality say at this point? The inequality should somehow point out that that's not very good, because we don't know this in a practical problem. We only know this. The other way around. We know this, but we don't know this. So the question then is to analyze it. First we calculate the error. I'm going to illustrate this, so I want to know where does this actually sit, since we know it. We'll do this first, and then we'll calculate these two things. And we know the condition number from before. So what have we got? The only thing we don't have from before is the residual. Error. The other way around. Minus 1, minus 2. Minus 1. Norm of E is 2. Norm of X is 1. So the inside of the sandwich is 2. Yeah.
Do we always take the top value of the vector? Yeah, sorry, when we were determining the absolute value of the error equals 2, we took 2 instead of 1.
We do the row sum norm. The row sum norm.
Oh.
Right? So we calculate the sum of the things in the rows, and there's only one column, so it's just the column. You take maximum. They're using magnitudes, absolute value. So in effect, with a vector like this, it's the largest absolute value in the vector.
Okay.
We have the inside of the sandwich. We need to write the inequality, residual, ax hat minus b. Remember the definition of the residual, that's important. It's the difference between ax and b, where x is x hat, the approximate solution. Which, if it was exact, it would be 0. So you can calculate it, multiply it out. There's a x hat minus b. And that is 0 minus 0.01. Norm is the biggest value in the vector. There. And so norm of R, the norm of V, the relative residual is, can everybody see this in the back? Can you see okay? This is an important line, it's the conclusion. This is 0.01 over V, which is 1. So this is pretty small. This guy, nice, small. 10 to the minus 2. 10 to the minus 2. Kappa is 1197, 10 to the 3. So we have 6 orders of magnitude from the kappa. Already not good. That's from the previous problem. Inequality. Put the numbers in this. This guy is that. There's relative error. And here we get 1197 and 4.01 again. And those numbers translate to 10. I've given it in orders of magnitude. 10 to the minus 3. So this guy. This is 10 to the minus 2. minus 2. That's 10 to the minus 5. And 6 orders of magnitude remain between the two sides. And where does our actual error that we calculated fit? Where does it go? Here, 2. 2 over 1. This is in red. Two. So it's closer to this one. But if I didn't know that too, I said, can you interpret this? You wouldn't be able to make any conclusion at all. Despite the fact that the residual is small, the condition number is large enough, even when it's only 10 to the 3, to produce a useless result. It could just as easily have been down close to this number. Any questions? Yes?
What's the difference between just regular E and like the relative error?
The E is the error, it's a vector, here it is. The
And most
relative error is the size of this vector compared to the solution. So it's giving it some interpretation.
Okay.
So that's a scalar, the relative error.
Okay. Thank you.
Comparing sizes. Any questions? That's kind of a downer that doesn't give you always a good thing. Sometimes it does. But it does point out the necessity for keeping the condition number small when doing computations. And small, it doesn't mean less than 10 to the 10. It means as small as possible. And there are some things about this which I'm going to mention. The rest of this is all practical stuff. I call it other observations, or concluding remarks, whatever you want to call it. It kind of ties together a few things. There's a result stated in the box which is not easy to prove. It's not even proved in the purple book. It's quite difficult. Apparently, I've never seen a proof of it. It's kind of a tricky one to state, but what it says is that very useful rule of thumb. And when you're solving AX equals B, you can say that the condition number will tell you approximately how many significant digits you lose in floating point arithmetic. So for instance, if the condition number is 10 to the 3, that means that the last 3 significant digits in your answer are quite possibly corrupted by error. If your condition number is 10 to the 8, that means you've lost 8 digits to possible error in your answer. And how many digits do you have in floating point? 16. In other words, you've lost a lot of digits. So the goal is to keep the condition number small just for that reason. And this is one thing I sometimes put this in exam problems. Approximately how many significant digits are possibly inaccurate in this, given the situation where you've already calculated the condition number. It's like an extra part to the problem. That one is one of the types that often causes trouble, just because it doesn't sink in. It's like I've made a remark about it and then it'll go over. You won't remember it. So you need to keep a note somewhere that that's an important thing to remember for the exam. But it's a rule of thumb that works. Condition number, order of magnitude, tells you about how many decimal digits of accuracy you've lost. That's the result. And when you're doing problems, sometimes I'll give you a matrix and you're asked to use, on paper, do calculations with reduced digit arithmetic. So either you round or you chop, one or the other. And in the test, you'll be told which to use. It doesn't really matter because it's all order of magnitude stuff anyway. But What it means is that, say you're doing Gaussian elimination, every time you do a calculation, you round the answer off, which is and it'll be maybe to 3 significant digits, something like that. So in other words, you're doing floating point arithmetic with reduced digits because you don't want to be using huge numbers on test paper. And it illustrates it on paper. So in other words, you're magnifying the situation to make the problem reasonable. It just means use every step of every calculation, pretend you're doing it in floating point, but you've only got 3 digits or 4 or whatever it tells you to use. Round them off. There's a little example coming up in a moment of this. So that's what that means in examples. Use reduced significant digit arithmetic. That's kind of the problem you might expect to get. Second other observation is that we can answer the question now why pivoting is so important for Gaussian elimination when you're using a computer. We said that, but we didn't really explain why. And it's take back just to the beginning of the Gaussian elimination. You've got a system, AX equals B. You write A and B as the augmented matrix. And then you do raw operations to get it to echelon form. What is the objective when you're doing that? In sort of an overarching way, what is the objective? The original system, if I said to you, what's X? You look at it and there's no way to know. You have to kind of do calculations. If I go over to the echelon system, I say, what's X? You can sort of almost do it by inspection. What you've done is, you've taken a system which is not easy to see what X is, and you've converted it step by step into a system. At each stage, it's supposed to have the same solutions because you've done your raw operations properly. And at the end, you've got it into a form which has the same solutions as the original one, but they're very easy to spot. You just do back substitution. Or if you've gone even further, you've gone to Gauss-Jordan, you can just read them off the answer. But at every stage of Gaussian elimination, you're supposed to be doing a situation where the solutions have not changed. And that's where pivoting becomes important when you're doing it using floating point arithmetic. Because if you've got a problem with the condition number, you've got a problem with your answer. You just know that you've lost digits. So an example is here. I like this example because it's simple and it illustrates the point. It's gone. Yeah, we've got enough time to do it. Remember, what we're doing here in this little section, number 3, is all practical stuff. This is what I said about the first point, especially this. Don't forget that. Number 2 is what I just said. And it's not just a little thing, it's any numerical implementation of Gauss elimination must include pivoting, or else it can lead to errors very simply for very simple problems. It's not just like a fussing to get extra accuracy. It's quite important to get any sort of meaningful answer in many cases. Let's do an example. So the question says, solve using 3 decimal significant digits and arithmetic at each stage using Gaussian elimination, A without, B with pivoting. And I think I rounded it. It would say if it was an exam problem. A, no pivoting. Okay. First, we need AD, the elemental matrix. There it is. First step. First step, I multiply by 1,000 to get rid of this small thing. I'm doing it freely, no pivoting here. Yes. Question.
Would you be able to read observation number 1?
Well, I was just summarizing what I said. It's on the slide notes that I gave you, the notes that are on the,
Okay.
in more detail. It just says that the rule of thumb is that you lose, if the order of magnitude of kappa, that's how many decimal digits you lose when you're doing the AX equals B solution.
Okay. And what does DEC stand for? The very first word you wrote for observation.
Decimal digits.
Oh, okay.
Decimal digits in floating point arithmetic. Okay? The first step here, I multiply by 1,000. No. This is 1 minus 1. Two, 1, 0. This is row 1, it's row 1, times it down. Now we get a 0 down in the corner here. I didn't have to do any rounding there because there was nothing to round. Here I will. Row 2 gets row 2 minus 2 row 1. I'm going to get 0, 2,000, and minus 2,000. And that is 2001, 3 digits. I've rounded it to 3 digits. Okay. And then we'll divide by 1,000. 1 minus 1. 2, 1 minus 1. Row 3 gets row 3 divided by 2,000. And now I can read off my solution and get 0 minus 1. So the answer that we get without pivoting. With pivoting. Look at the original system. Tell me which row got the smaller coefficient for the, oh, I wrote that off. Doesn't matter. With pivoting. back to the first matrix. Which of these is the smallest? It could be a macro question. Which is the smaller for the pivot? Yes? This one?
The 2.
Which is smaller number?
Which one's smaller?
Yeah, that one. So that's going to be the pivot, right? We have to do a row interchange. That row goes to the bottom.
This stuff completely over my head. Wait. Divided by negative 2,000. No, I think just 2,000.
For the pivot, we choose the larger, or largest, if there's more than 2, thing in the available pivots. And that would be 2. So row 2, row 1, get interchanged. There's no rounding to do at that stage. Next step, we just do the row operation. And you get 2, 0, 1, minus 1, 1, 0. And the row operation is row 2 gets row 2 minus 1 over 2,000 row 1. This is what you get. And I note on here that this minus 1 is minus 1 minus 1 over 2,000 rounded. So we've still had to do a rounding at that point to 3 digits. I've replaced this by this. We lost the 1 over 2,000 bit. Solution. 1 over 2 minus 1. Different. This is just magnifying what goes on in the final decimal places with regular floating point arithmetic. The exact solution is this number and this number. Which is better? Similar. Second number is not bad for either, but that one is much better than this one. And that's the effect of the not using pivoting. That shows that it happens. Why it's important. It's a pretty simple problem. It's a little bit sort of imaginary, the problem, but still, it illustrates what goes on in floating point. Why does it happen? We didn't answer that yet. When we see it, it's there, it's happened. Pivoting improves the situation. Why does that happen? Remember I said you start with the system, you row operations, and you produce a system which has, at each stage, the same solutions by doing the row operations properly. That's how Gaussian elimination works. So something has gone awry here. And the problem is, that it can be very easily stated. If you look at the condition numbers, at each stage this represents a system. This is the original one, there's a new system, a new system, a new system. And they each have their own condition numbers, even though they're supposed to have the same solution. Look at the condition numbers. This one is 3, the original system. You can check these condition numbers of the coefficient matrix. Just put it into math and check. This one, kappa is 500, so it's getting big already. Or if you like, its order of magnitude is 2, so we've lost 2 digits. And we're doing rounding to 3 digits, so you can see where the problem comes up. Next one, condition number is 3000. It's now 10 to the 3. That means that because of the condition number, whatever we do as far as a calculation involves rounding, we are going to lose all our digits. At that point, the system becomes almost unsolvable in our reduced floating point system. And then now look at the last one. Kappa is 10 to the 6. This is purely a consequence of not having done pivoting. Condition numbers for these look much better. This is 3. This one. 2. This one. It's 2. And the only thing that's different in these is we used pivoting. And without pivoting, the condition number grows uncontrollably and produces possibly a system which defeats your floating point system even. And that's why it's extremely important to use pivoting. In all algorithms, pivoting is mandatory. Don't include it for computational algorithm. You have trouble. Does that make sense?
Yeah.
That kind of ties together some of the past things we've been doing, right back to the Gaussian elimination. I like that example. And there's one final remark here to discuss, and that's scaling. I think with this example, the best thing to do, rather than me writing it all up on the board, numbers and things, you can see it when you get these notes. I'll put them on learner. But did I already do it? No, right to the end. I think it would be called number 9 or something. File name.
I
I don't see it.
9B, 9A. No.
I saw 9A, but not
Okay.
8.
Well, 9B you need to get. But on the last page of the notes, there's a numerical example, again using reduced arithmetic. It says, solve AX equals B. And this final observation is called scaling, and in the example, imagine this is data from some electrical experiment you were doing, or biological experiment in your case. Maybe the pressures or something like that. Here's our system, AX equals B. You're asked to solve it using 5 decimal digit arithmetic. Decimal digit arithmetic. And this serves as a practice problem, if you like, as well, because you can do it yourself and see that you confirm that your answer is consistent. And what's it all about? Well, look at the first column. Imagine there were data from the experiment. It causes difficulties to numerical solution because this one is so much different in order of magnitude to the other numbers in the matrix. And so what you do is you adjust it by using the SI prefixes. And so for instance, if this was meters, you would change it to millimeters, and then these numbers become closer to these, like it was picofarads or whatever. Like that's one of the extreme useful uses of the SI prefixes, is that you can make matrices look better. And that's called scaling. It works where one column is much different from the rest in order of magnitude. Scaling says column 1 is adjusted, multiplied by a factor. So we can have a new system, and the new system would be with this matrix. And solve the new system for some different answer equals b, and then convert y, get x from y. And what would it be in this case? Y. And when you do that step, it's always backwards to how intuition thinks. Because you've multiplied these by the relationship between x and y is backwards to what the intuition will tell you. Just be careful with that. Best thing is to do the problem, you'll see why. By creating this, you effectively change the x1 value. And you've got to multiply it by 0.01 to get it back, to get to this point, so that you get the same system. Okay? And so then I went through and showed you here. I'm going to solve it using 5 decimal digit arithmetic, use pivoting in the scale column 1. So we scale column 1, we go ahead and solve that. And this example illustrates the idea of reduced digit arithmetic again. And then at the very end, it shows you the differences in the actual floating point numbers with the 16 decimal digits. Do you know how to get that in MATLAB? How do you see all the digits? Do format long. That will show you the full 16 decimal digits of the floating point. And if you do format hex, it'll show you the hex codes, and you see exactly what's stored for those digits. So this is good enough to illustrate examples. But when I solved this, I solved it with scaling, and I looked at format long, and I found all the digits, and I compared them. And the condition number of this matrix is, I don't know what it is. That's not really what this is about, though. It's showing you that pivoting is not necessarily, like in this case, the whole column was out of whack with the rest of the matrix. But sometimes you'll end up with a 0.00211 in here. This number is much smaller than the others, but it depends to some extent on what's here. So there's a thing called scale pivoting, which looks at the ratio of this to the other things in the row and decides. So it might pick, say, something which is not necessarily the largest thing in the row. It might be something in between, but it's larger in relation to the other things in the row. That's called scale pivoting. And that is not part of this course because it's not, I mean, it's useful, but it's not a sort of mainstream thing. This operation of scaling a column is mundane. If a column is like this, do not proceed because you'll get that potential error. There's lots of very plain examples showing data that's been collected where, for instance, there's data, I've seen an example where there's data which shows something being measured on a yearly basis, and if you use the number of the year as your X data, you get a matrix and you have to solve the system, and that has a very large condition. If you say that you're going to use the how many years past the present year it is, or before the present year, the numbers are smaller. They've changed now by order of magnitude 10 to the 3, and that reduced the condition number. And the one with the year numbers gave quite inaccurate results, but not very big system, using MATLAB. And by using very carefully, in effect, scaling that so that the matrix is roughly the same in all its spots, That's a mundane, everyday thing which you might have to do to manipulate your data before you go ahead and solve the problem. That's the kind of thing you do in engineering. It's not a mathematical thing. It's practical. You want to get an accurate answer. Some of the things we've been doing here are actual, like this whole section is important that you get the take-home messages from it. It's not just a question of doing the exam problem. Any questions? You're going to get to see algebra again. Systems design get this course and they get another linear algebra course later.
So we won't be given any formulas on the exam, right?
No.
Okay.
No.
Thank you
The
very much.
formulas to remember are the ones I've said in lectures. And in this whole section, there's the one inequality, the first one, the definition of kappa, which is easy, the norms, and apart from the first inequality, the one we did today, and then that rule of thumb, those aren't really formulas. There's really very little. Trickiest one is just that big one that I wrote on the board today. You've gone over time by 1 minute.
Did you try to write them right?
No, I don't think so.
Any more
I'll just
classes
use
today?
them.
Good. Go home and enjoy the spring weather.
Thank you.
I believe